Okay, let us start. So, in the last lecture we saw a simple application of the Radon-Nikodym theorem, right, which gave us polar representations for complex measures. So, we will continue along these lines. We will see some more applications of the Radon-Nikodym theorem. Okay. So, let us start. Okay. So, let me state this as a theorem. Okay. So, as usual we have a space X f. Okay. Since, well, we will assume that it is a positive measure. Suppose mu is a positive measure, okay, and let us say G belongs to L1 mu. Okay. So, G can be complex valued. Okay. So, define. So, we are going to define another measure. We have seen this before, lambda of E to be integral over E G d mu. Okay. Then of course, lambda is a complex measure, right. Then lambda is a complex measure. This we have seen. This we have seen before. Okay. So, the assertion is that mod lambda of E equal to integral over E mod G d mu. Okay. So, the lambda is given by G, mod lambda is given by mod G. Okay. So, this is sort of you can write it like this, d lambda is equal to G d mu, right, that is the given condition. Then d mod lambda is mod G times d mu. Okay. So, mu is a positive measure of course. Okay. So, that is simply taking the modulus on both sides, right. So, symbolically that looks sort of very nice, but with this requires a proof, right. It is not, because mod lambda is defined to be the total variation. So, you take a measurable partition and then add up things and take the supremum, right. So, how do we know that we are getting mod G? So, that is where the previous theorem will be very useful. So, let us write it as a proof. Okay. So, first of all there exists H such that mod H equal to 1, right, and d lambda is equal to H times d mod lambda, right, because lambda is a complex measure we can do this. Okay. But okay, d lambda we know is equal to G d mu, right. So, that is what is given to us, right. So, in symbolic form d lambda is equal to G d mu, which is same as saying lambda of E is integral over E G d mu, okay, which of course d lambda is given by H times d mod lambda. Okay. So, you multiply by, so we have a equality. So, multiply by H bar on both sides, okay, on both sides. So, this does not make sense actually, but I will explain what this means. So, this is a symbolic calculation. So, let us say symbolic calculation which has to be justified. Okay. So, this is only to motivate what happens here. So, if you multiply by H bar on both sides, so let us take this one first. I multiply by H bar. So, I will have H bar H d mod lambda. H bar into H is mod H square, but mod H is 1, right. So, d mod lambda. So, this is d mod lambda. So, on this side you get d mod lambda, on this side you will get G times H bar. So, we are going to get d mod lambda equal to G H bar d mu, right. That is what we should be getting if you multiply by H bar on both sides. Okay. But this has to be justified, right, because we just multiplied on some symbols we just multiply. Okay. So, let us try to understand this. Why is this true? Okay. So, let us take some space here. Okay. So, what do we know? We know that integral over E G d mu, okay, equal to integral over E H d mod lambda, right, because this is lambda E, lambda of E. Okay. Okay, let us write this in a slightly better form. Lambda of E equal to G. So, that we know, right, because that is the equality here, right. So, write it in a slightly better form. So, I have integral over x chi e times G d mu equal to integral over x chi e times h d mod. Okay. So, from chi e we can go to simple functions, right. So, from here we go to simple functions. So, from chi e go to simple functions, and so what do we get? So, we will get integral over x s g d mu equal to integral over x s h d mod mu, right, s simple function, okay, because that is just a linear combination of chi's, right. Okay. Now, you take, okay, so just be careful here. So, take f to be a bounded function, okay. Then I know there are simple functions converging to f uniformly, if you like, right. For bounded measurable functions we always have that. Then you can apply dct to it. So, we have this equality for each Sn, right. So, you can look at Xn. Now, we are dealing with finite measures and G d mu is in L1. So maybe let's write this clearly. So, let us look at x Sn G d mu. Where is G? G is in L1 mu. Sn converges to f. F is a bounded function. Okay. So, this is uniformly. This converges uniformly. So, Sn times G in modulus is less than or equal to, Sn's are all bounded, f is bounded. So, you will have some constant times mod G, but this is an L1 function, right. So, I can apply dct. So, apply dct, I will get integral over x f g d mu, right. Similarly, on the right hand side, so this is equal to, I will get x f h d mod mu. I will leave it to you why this converges. So, again apply appropriate dct. So, this is true at least for f bounded. Okay. Now, you have to do is to change f to f times h bar, right. Mod h is 1. So, h bar is a bounded function. So, you will get what you want. So, well, what do you get? You will get that. So, let me write it down as one more line. So, we will have integral okay. So, change f to, okay, let me see the thing. Okay. So, we want to show that d mod lambda is equal to g h bar d mu, right. So, okay. So, if I change f to f dot h bar, so I will have f h bar g d mu equal to h bar into h is 1. So, I will have f d mu for all, at least for f bounded. So, f bounded. So, I can take f to be chi e, right, take f to be chi e. Well, what do you get then? Then you get integral over e h bar g d mu is equal to integral over e d mod mu, right. So, this is what is symbolically written as h bar g d mu equal to d mod mu, right. That is what I meant by multiplying by h bar on both sides, right. This is what we wanted to prove, right. Okay. So, okay. So, I mixed up my mu and lambda. Okay. So, just be careful here. So, we are starting with g d mu equal to h d mod lambda. Okay. So, everywhere you have to change to d mod lambda. Okay. So, anyway, there is no mistake in the proof. It is just that instead of writing mu, I wrote lambda. So, instead of writing lambda, I wrote mu. Okay. So, anyway you can correct this. So, there is no mistake in the proof. Okay. So, multiplying by h bar we obtain d mod lambda equal to g h bar d mod mu, right. This is what we obtained. Okay. Hence 0 less than or equal to integral over E d mod lambda. Of course, it is a measure of E with respect to mod lambda. This is equal to, well, whatever we have just proved, right, we use this. So, integral over E g h bar d mod mu, okay, very nice. But what are we saying? We are saying that this is positive, right, or greater than or equal to 0, which means if mod mu of E is positive, then 1 by mod mu of E integral over E g h bar d mod mu, this is positive, okay, which means the averages are positive. You can use that or simply look at the integrals. I think that is easier because we are not assuming anything about mu. So, simply look at the integrals. Integrals are positive. So, what I want to say is you can leave it, think of this as an exercise. If I have f in L1 of mu is a positive measure. I am not assuming sigma finiteness or anything, it is just a positive measure, and if integral over E f d mu is positive or non-negative for every E in the sigma algebra, okay, then to consider this as an easy exercise, then f itself is greater than or equal to 0 almost everywhere, right. For example, f can be complex valued, but if you write f as real plus I times the imaginary part is integral 0, all the integrals 0, so it will have to be 0, and so f is real valued and all the integrals over subsets of x are also positive, so f will have to be positive, okay. So, that's an easy assertion, and what we have got is that g h bar has the same property, that it is positive, okay. In this case you can use okay, why do I keep writing mod mu? Mu is positive, right. So, I can write just mu, okay. So, I am making silly mistakes, okay. So, this is a positive measure and I have a function whose integrals are positive. So, this of course tells me that g h bar is greater than or equal to 0 almost everywhere, and you can redefine it. But if it is greater than or equal to 0, it will be equal to its modulus, right. But h has modulus 1, so you get mod g. So, the Radon-Nikodym derivative here is actually mod g, that is all we want, right. So, let us go back, since I made some silly errors. We are trying to prove that the Radon-Nikodym derivative of mod lambda, right, is mod g if the Radon-Nikodym derivative of lambda is g. So, finally, that is what we have got. If you look at mod lambda of E, the Radon-Nikodym derivative is g h bar, but g h bar is positive, so it is equal to its modulus, and so it is mod g, okay. So, that proves the theorem. There are other consequences. So, let us do one more of that. This is called the Hahn decomposition or Jordan-Hahn decomposition. So, we saw something very similar earlier, but we are trying to deduce it from the Radon-Nikodym theorem, okay. So, let mu be a real measure. So, now I am not assuming it's complex valued, it is real valued, or it's, so in our nomenclature it is a signed measure, right, it is a signed measure, okay, on some space of course xf, okay. Then there exist sets A and B in script f such that the space X is A union B and A and B are disjoint, okay, and the positive and negative variation, the positive and negative variations of mu. So, what are they? They are denoted by mu plus and mu minus. So, we had defined this, remember, they satisfy mu plus of E is mu of A intersection E. So, remember A is this, we have A and B which are complements to each other, right, disjoint sets, and mu minus is mu of B intersection E, okay. That is why they are mutually singular, right. So, mu plus is mutually singular to mu minus, and mu is mu plus minus mu minus. Remember, this was very similar to the positive and negative part of the functions, right, and mod mu was the sum of them, okay. So, that is how we had defined this, okay. Well, let us prove this. So, let me draw some easy picture here. So, this, the space X gets divided into two parts, okay. So, I will have A here, I will have B here, and mu plus is something which is concentrated here, okay. So, this gives me mu plus and whatever is here gives me mu minus, okay. So, this portion gives me mu minus, right. It is the restriction of mu to A which gives me the positive part, restriction of mu to B gives me the negative part, okay. So, let's prove this. So, proof. So, we know d mu equal to h d mod mu, right. Mu is a real measure. So, mod mu is a finite measure and h has the property that mod h equal to 1, right, for every x. So, now mu is real, So, the Radon coordinate, so when I integrate over any set, I am going to get a real number, and so averages of h are real, so implies h is real, right. So, mu is real implies h is real. So, you can use the averages result if you want, averages of h belong to the reals, right, and R is closed in the complex plane, right. So, the closed set you take to be the reals and you have a function whose averages are inside real numbers. So, the function itself will be real, right, almost everywhere. Of course, you can redefine it so that it is real. So, it's real almost everywhere, but mod h equal to 1 and h is real. So, the only real numbers whose modulus is 1 is plus or minus 1, implies h equal to plus or minus 1 real almost everywhere, okay. So, we can redefine it. So, this is the usual thing, redefine h so that h of x is either 1 or minus 1, right. So, that requires only redefining it on a set of measure 0. So, on that set of measure 0 you define it to be 1, okay, that will do. Alright. So, now it is clear what you should do, right. So, the Radon-Nikodym derivative is positive on a set and negative on a set. So, the positive part should be given by the set where the Radon-Nikodym derivative is positive, okay. So, define. So, what remains is easy to see, define A to be the set where the Radon-Nikodym derivative is positive, but it is 1 of course, and B to be the set where it is negative, hx equal to minus 1. So, all the properties of A and B are true, right. So, A union B is the whole space, right, because h is either 1 or minus 1 and A intersection B is empty, okay. So, that is true, okay. So, I need to look at what happens to mu plus and mu minus. So, remember mu plus is mod mu plus mu divided by 2, right, and mu minus is mod mu minus mu divided by 2, right. So, let's look at mu plus. So, since mu plus is equal to half mod mu plus mu. Okay. So, how will I write mu plus of E? So, mu plus of any set E is of course half times mod mu of E plus mu of E, correct. Okay. So, this is the easy part, okay, which is equal to half times integral over E d mod mu plus integral over E. Remember mu is always equal to h times d mod mu. So, I am shifting everything to d mod mu. Okay. So, h times d mod mu, okay, which is equal to, so half integral over E, well it is just 1 plus h d mod mu. Okay. So, what happens to 1 plus h? Well, 1 plus h is, h takes either 0 or 1, right, either 1 or minus 1. So, h of x is either 1 or minus 1, right. So, this is for x in A, x in B. Okay. So, 1 plus h will be 0 for x in B, right. Okay. So, I can write this as integral over E intersection A, okay, 1 plus, so integral over E intersection A and integral over E intersection B. Okay. So, that will give me integral over E. But what happens to 1 plus h by 2? So, 1 plus h by 2 equal to 1 equal to h on A, right. So, whenever I have A subset of A, 1 plus h by 2 is h. So, I will write it as h, it is 1, but I will write it as h d mod mu because I want mu to come, right. And here it is 0 d mod mu, it does not matter what measure we have there, right. So, this is simply h d mod mu is mu, right. So, this is d mu. So, this is mu of E intersection A. Okay. So, I wrote everything in detail so that it is clear what is happening. So, mu, we started with mu plus of E and we ended up with mu of E intersection A, which is precisely what we wanted to prove. So, the restriction of mu to A will give me mu plus, and similarly mu minus. If I look at mu minus, instead of the plus I will have minuses, right, and I have 1 minus h by 2 and 1 minus h by 2 equal to 1 equal to h on, or minus h on B. Okay. So, minus h on B. So, that is all is needed there, and you will have the result. Okay. So, that proves the this is called the hand decomposition, and since mu plus and mu minus are sort of unique, you know the sets A and B are unique up to sets of measure 0. Of course, you can add, you can take something from B which is of measure 0 and add to A, it will not change anything. Okay. Okay. So, we have a immediate corollary to this which gives a property of mu plus and mu minus. So, if mu equal to lambda 1 minus lambda 2, okay. So, lambda 1 and lambda 2 are positive finite measures. Okay. So, if mu is real, then I know to write mu as mu plus minus mu minus, where mu plus and mu minus are positive finite measures. This is an arbitrary collection, okay, lambda 1 and lambda 2. Then lambda 1 is greater than or equal to mu plus and lambda 2 is greater than or equal to mu minus. So, these are the smallest positive finite measures you can get. So, if you have seen functions of bounded variation and so on, you know how to write this as a difference of two increasing functions and things like that. So, there you see total variation and of the bounded variation function and so on. So, it is very similar to that. Okay. So, the minimal property of mu plus and mu minus, in fact, it is related to that, right. We will see that the absolute, when we study absolutely continuous functions, we will see that. Okay. But proof of this is one line. So, both mu plus and mu minus have a minimal property, right. So, since mu is less than or equal to lambda 1, why is mu less than or equal to lambda 1? Because mu is equal to lambda 1 minus lambda 2, which is a positive measure, right. So, I am subtracting something positive. So, mu will be less than or equal to lambda 1, So, mu plus of E equal to mu of E intersection A, right. A is my set which we defined earlier, where the Radon-Nikodym derivative is 1. This of course is less than or equal to lambda 1 of E intersection A, because mu is less than or equal to lambda 1, which is of course less than or equal to lambda 1 of E. Okay. So, mu plus is less than or equal to lambda 1. So, that is the first thing. Similarly, second one. Similarly, second assertion can be proved. Okay. So, I will leave it to you. Okay. So, this is a good place to stop. So, we saw two consequences of the Radon-Nikodym theorem. One is the polar representation for a measure, well in fact three applications, polar representations, and if I have a measure defined by an integral, then integral of g, let us say, then mod g will be the Radon-Nikodym derivative for the corresponding total variation measure, and we have seen the Hahn decomposition. Okay. So, well we will continue with this, we will continue studying complex measures. Our next aim is to look at the continuous linear functionals on LP. So, if you go back to the proof of the Radon-Nikodym theorem, we use the fact that any continuous linear functional on L2 is given by an inner product. So, inner product here would mean simply you are integrating against another L2 function. Now, 2 and 2 are conjugate exponents, because 1 by 2 plus 1 by 2 equal to 1, and when we go to LP we will be integrating against an LQ function, which where q is the conjugate exponent of p, 1 by p plus 1 by q equal to 1, and that will characterize the continuous linear functionals on LP. So, that is what we will do in the coming lectures. Okay. So, we will stop here.